Hello, good afternoon, and welcome to the IPX session. Innovation Program X, it's about exploratory research, disruptive innovation, and system architecture. Technologies such as artificial intelligence and blockchain are bringing disruptive changes to a variety of sectors. The research projects within IPX are looking into how such technologies could be applied to the rail sector to support functions such as automation, network management, maintenance, and how this would impact its operations, safety, lifecycle cost, and finally also improve the customer experience. I hope that you will find this webinar informative and useful. Thank you for joining us. But before we start, I would like to give you also some housekeeping rules. First of all, to ensure a smooth session and to avoid any technical difficulties, we have disabled the microphones and the cameras for all participants. But of course, we want to hear from you, also your thoughts or questions. So please use the chat function at the end or also during the presentations to ask questions. We will most likely address approximately 2 or 3 questions per project. Please also note that the sessions are recorded and will be available on Europe's Rail website in the upcoming days. To be able to join the next sessions, you simply have to visit Europe's Rail website and click on the Join link in the Innovation Days program. Please be aware that each session has a different link, so don't come back to the current link to attend other sessions. We would also like to invite you to comment on how we can improve our events in the future, and that dedicated survey will be available on our website on Friday, 9th December afternoon. So please do not hesitate to take part. Finally, you're also invited to subscribe to our mailing list by visiting our website. Like this, you will receive the final takeaways of the event, including the survey and the recordings. I would then pass the floor directly to the Rails project, to Valeria Vittorini, who's an associate professor of computer engineering at the University of Naples Federico II. Valeria, welcome, and please, the floor is yours.
Thank you. Thank you so much for your introduction. I would like to provide you all with some information about the research we are conducting in Rails, investigating the potential, the opportunities, and the challenges of using artificial intelligence in the rail industry. So please go to the next slide. Okay, thank you. The goal of Rails is to design some roadmaps that can support the development and the adoption of applications based on artificial intelligence models and techniques. As such, Rails has broad scope, and of course, we had to restrict our investigation to meaningful application areas. Specifically, this presentation focuses on autonomous driving, smart maintenance, and traffic planning and management, and on some innovative aspects along these directions, as you can see from the outline. So next. The project involves 4 partners from Europe, 2 computer science institutions, SINI, that is a consortium of Italian universities, and the Linnaeus University in Sweden, and 2 transport institutes, the Leeds University in the United Kingdom and the TU Delft University in the Netherlands. Different speakers from the research group will present today, namely the project's technical manager, Professor Francesco Flammini from the University Linnaeus in Sweden, and 2 young PhD students that are carrying out the research activities in Rails, Lorenzo De Donato from SINI and Rui Van Tang from the University of Leeds. Next, please. As already mentioned, the Rails main goal is to provide roadmaps towards an effective adoption of artificial intelligence in railways, and at this aim, some macro objectives are the identification of the potential of artificial intelligence for railways, the recognition of required innovation shift, the development of methodological and experimental proof of concepts, the development of benchmark models and simulation, and at these aims, the proof of concept are our benchmark or the proposed benchmark that we have selected, the involvement of relevant REL stakeholders, and the training of young researchers, and this is the reason why we have 2 PhD students working at the research activities. So next. As already mentioned, RELS is based on 3 main pillars, and they are the rail safety and automation, the application of artificial intelligence to predictive maintenance and defect detection, and the application of artificial intelligence to traffic planning and management. The path towards the objectives I illustrated before includes some steps. First, a taxonomy of artificial intelligence concept has been developed, and the state of the art as well as state of practice has been performed. Then several case studies have been identified, and some proof of concept are now ongoing, including the necessary gaps and problems to be overcome. I quickly go through the results we achieved in the first phase of the project. On these results, in fact, is based the research that will be presented in the following of this presentation. Next, please. Many different definitions of artificial intelligence are available, as you know. Here is the one we proposed and adopted for railways because it focuses on some aspects that are meaningful according to us to the rail domain. And so for our purposes, artificial intelligence is the discipline gathering all the aspects that allow an entity to determine how to perform a task and or take a decision based on the experience measured by observing samples and or by interacting with an environment. So experience, for example, and environment are 2 keywords for our work. Next, please. There is then there is the need for a clear distinction between different concepts when dealing with artificial intelligence. Here, the artificial intelligence is considered as a discipline, and artificial intelligence research fields, artificial intelligence applications, and artificial intelligence techniques are clearly separated. We did an effort to provide this taxonomy that you, of course, can find in our public documents. Please, next. Then we try to define the application, the railway application domains in which artificial intelligence is applied in the literature, and the relevant railway problems to be investigated by means of artificial techniques. And we identified some application area that are outlined with different color in these slides, and of course the same color is reported to provide a mapping between a railway domain and the related problem to be investigated by using artificial intelligence techniques. And so this color have a meaning also in the next slide. Next slide, please. Okay. So here we can see how the scientific literature is placed in this moment, and the existing research applying artificial intelligence in railways has been considered. Notably, the most investigated field is maintenance, while revenue management and transport policy are quite neglected in the scientific literature. So you can see on your left the different railway domain investigated with artificial intelligence techniques in descendant order. And on your right, you can see some artificial intelligence approaches applied to the different research domain in railways. Okay, next. Okay, and the regulatory landscape and the need for trustworthy artificial intelligence are important aspects when dealing with the artificial intelligence for critical system. Artificial intelligence, of course, opens new scenarios and great opportunities for railway system, but on the other hand, it raises many issues regarding system safety, dependability, security, and new threats associated with a high level of autonomy. So also the different guidelines, regulations, standards, and from different bodies have been reviewed. Next, please. According to a survey we conducted among stakeholders, in fact, safety, dependability, and trustworthiness and related issues are the main challenges to cope with, followed by the lack of proper dataset for training, testing artificial intelligence models, and the lack of specific standards and regulation. So far, I tried to provide the background research on which the current work is based and provide you with a quick picture of some introductory aspects. And now I give the floor to Professor Francesco Flammini, who is the Rail Technical Manager.
Thank you, Valeria. Good afternoon, everybody. So this part of the presentation will be focused on the use of artificial intelligence for autonomous driving. Next slide, please. Okay, so the main paradigm here is the switch from automation to autonomy. Automation, of course, is not a new concept in railways. You have autonomous train control, which is a combination of automatic train operation and automatic train protection. And this is used in many railways, including driverless trains. But if you want to make the system fully autonomous, then you need a paradigm shift, and this paradigm shift needs the contribution of artificial intelligence, machine learning, in order to make the system learn from experience and adapt to possibly unknown scenarios. Next slide, please. Okay, so one thing that we did and was important part of the project was the investigation of autonomous vehicles in other transportation domains, for instance, avionics and self-driving cars. And we discovered there is maybe not many working applications, but quite a lot of research that has been aimed at characterizing reference conceptual architectures and even software architecture for self-driving vehicles. For instance, you can see in this slide how there is this distinction between the sensing layer, the perception layer, and the decision layer. And there is also this important part on top that is the connection to the cloud, which is something that is important to formalize how an autonomous system should work and can be transferred to railways. So part of the activities that we have performed regarding autonomous and cooperative driving was to understand which results from other domains could be transferred to railways. Next slide, please. And one thing that we discovered is that there is an ongoing research in automotive that is based on the so-called safety envelopes that are based on the doer checker paradigm. So you have part of the system which is free to use machine learning to optimize some of the system parameters and provide autonomy to some extent. And there is another part of the system which is the checker that has the responsibility to demonstrate that the system is safe. Which is not a completely new concept for people working in railways, because we have in many current railways the part that is related to automatic train operations, so not yet fully autonomous, but based on more traditional technologies. And then you have the automatic train protection, that is the part of the system that guarantees the safety. So next slide, please. So based on that, we made a formalization, a sort of a vision of what we think is the future intelligent train control that leverages on the automatic train protection, which is the safety technology that we already have as acting as a safety envelope. And then you can replace the automatic train operation with more intelligent train operations. So leveraging on learning and adaptation. And this allows us to perform intelligent optimization, for instance, of energy consumption or line capacity and passenger comfort, among other things. But we can do something more. I mean, we can add the so-called intelligent train protection. Adding intelligent train protection means that the system can autonomously recognize signals and obstacles, among other things. And this could be very important when you don't have automatic train protection, or when automatic train protection fails. So it could even be a temporary failure, or it can be some particular scenarios, such as the start of mission with the track ahead free, when the responsibility is given to the train driver. In this way, with intelligent train protection, you have an additional means in order to ensure system safety. Next slide, please. So what we try to define is on top of the grades of automation, we define the grades of intelligence. So railway automation, we know, and autonomy to some extent can be based only on traditional technology. So artificial intelligence and machine learning is not strictly needed. If you have, for instance, a completely segregated system with platform screen doors, as you have in many underground or railways or subways. But with intelligent train operation, intelligent train protection, you are actually adding something more. So from the basic grade of intelligence one, you can have traditional systems with limited or no autonomy, and you can gradually add intelligence to your system until a grade of intelligence 4, in which you have full implementation of intelligent train operation, intelligent train protection, with advanced learning and adaptation capabilities, such as the use, for instance, of unsupervised and reinforcement learning. And the other important thing here is the connection to the cloud, which allows the system to be fully connected and to get more information on, for instance, threats that have been experienced in similar systems worldwide, in order to enrich its knowledge base. Next slide, please. So the whole picture that you can get is what is represented in this slide, in which you have a fully connected architecture, in which you have trains and stations on the lower level, in which you can perform edge intelligence. Then as you move to the higher part of the system, you move from edge intelligence to cloud intelligence. At each level, you can have some autonomy, and you can use the digital twins and MAPE-K paradigm. MAPE-K stands for monitor, analyze, plan, and execute over a shared knowledge. And this knowledge is always growing as you move from the edge to the cloud. So this is a representation of a future railway in which you have this distributed knowledge and several levels of intelligence. Next slide, please. So which are the opportunities for artificial intelligence in intelligent train control? As we have seen, transfer from automotive to railways is allows us to divide the system. It's a very complex system and application into several layers, several parts that can be addressed and developed independently. And one important thing is that in order to make the system safe, you must not only consider signals and obstacles, as we have highlighted before, because signals and obstacles are of course important, but the safety of the system can be affected by other events that are not transferred to signals and are not only related to obstacles. For instance, the status of the system, what is happening around the system and even on board of the train, such as, for instance, anomalous vibrations or fire, must be detected by a specific set of sensors. So what you need is full environmental awareness in order to make the system 100% autonomous and safe. Next slide, please. Okay, regarding cooperative driving, what we have addressed in the project is the specific application of virtual coupling. Even virtual coupling is something that we can consider as a transfer from automotive to railways. In automotive, this paradigm is known as platooning, and it happens when you have more vehicles that are driving in cooperation with each other. So they are moving as they were a single convoy. And in railways, you do this by virtually connecting multiple trains. So you have trains that get very close to each other and move as they were a single train, a single convoy. In this way, what you can do is, of course, increase the capacity of the railway lines. Next slide, please. So, which are the objectives? As we have said, reducing the headways is a means to increase the capacity. We did an analysis to understand which techniques from other domains, specifically automotive, could be transferred to virtual to railways, so to virtual coupling. And one specific objective and one idea to that we are testing on this virtual coupling scenario is the use of reinforcement learning in order to implement a model-free approach. So learning by doing, learning from experience. When doing this, what we are experiencing, which is quite common problem and issue that you have when you want to implement machine learning in any domain, I would say, is the problem with the available data sets. So at the moment, we don't have an adequate data set that can be used. So what we need is to develop, and what we are doing is developing ad hoc simulators for the training and validation phases. Next slide, please. Okay, for this case study, which is the obstacle detection rail tracks, I will hand over to Lorenzo De Donato, who is one of the PhD students who is working on the project.
Okay, hi, good afternoon, everyone. And yeah, the purpose of this case study is to improve, let's say, the coverage of vision-based obstacle detection systems, which typically rely on supervised machine learning approaches. And these kind of approaches can detect only a specific set of pre-specified objects. Typically in complex scenarios like this one, which means obstacle detection on rail tracks, generic anomalies are detected by using other kind of sensors like radars or lidars. While vision-based systems are used to recognize the type of the object. However, the idea here is to understand to what extent it will be possible to leverage only cameras to effectively detect any kind of obstacles. And to this aim, this case study is an extremely interesting test bench given its relevance in the railway domain. But we also think that lessons learned from this case study can be applied also to other contexts like level crossing. So among the various issues, there are two main problems that should be tackled. The first one is that there are no, let's say, suitable dataset online, where by suitable we mean dataset reflecting specific task and domain characteristics, and for example, depicting like obstacles on rail tracks. So to overcome this, let's say, issue, we built a simulated scenario in Roadrunner, which is a MathWorks 3D editor. And if it is possible to run the video on the bottom right, yeah, this shows the scenario we created. So simulating a camera in front of the train. And here we can clearly safely put obstacles on the rail track and train and test the AI applications we are investigating. And here you can see like a car here on rail track. The other problem is related to the trustworthiness of AI systems in general, given the fact that it is not always possible to understand the reasoning behind the prediction of a specific deep learning system. And also that this system may also be unstable, which means that to a slight variation of the input, they could we could have very heavy variation on the output. So we are trying to understand how these issues can be mitigated also by, let's say, studying explainable AI approach. So next slide, please. So here is the general architecture of the system we are trying to develop. So in the first phase is to detect the rails, then post-processing crop out the rails area. And then in parallel, we would like to run two specific modules. One is the object detection module that will detect obstacles known a priori, while the anomaly detection module, which is the one we're mostly focusing on actually, is like in charge of detecting any kind of anomaly on rail tracks. Then we have like a merge detection module that will merge the two previous detections and a distance estimation to estimate clearly the distance of the obstacle from the train. So next slide, please. And up to now, we have focused on the realization of the rails detection module. But the problem here was that after having obtained the frame from the simulator, we had to manually label all of them. But it would have taken a lot of time. It is extremely time-consuming process. So we built like a semi-automatic labeling basing on transfer learning and self-learning. So the idea is to take a network, in this case, a deep learning neural network, in this case, a UNet, which is a network for semantic segmentation mainly, pre-train the UNet on an already existing dataset, which is a RailsM19 available online, and then label only 10% of the frames we extracted from the simulator and label the remaining frames by like using this algorithm for automatic labeling. Once we have labeled all the dataset, we applied some augmentation to like increase or decrease brightness, introduce a sun flare or rain, and so on. And then we train the UNet for the purpose we intended to use it, which means detect the rail track in frames, in video frames. Besides numerical results, the interesting thing is that this model here takes like 6.5 milliseconds to detect the rails up to now. And we would need to do some post-processing, but I mean, at the time it seems that it could meet some real-time constraints. So next slide, please. And these are some challenges and directions. So some final remarks on this part on AI for rail safety and automation. And we've talked about intelligent train control before, but when AI will be in charge of managing the safety of the whole system, Among the other things, we would need, of course, well-defined certification processes to understand possibly the safety integrity level of these systems, together with the trustworthiness, robustness, explainability, characteristics, and so on. And also, as Professor Fermini said, we, together with the mechanisms for environmental awareness, so obstacle detection and signal detection, even though they were completely trustworthy from an AI perspective, we will also need continuously monitoring mechanisms and self-awareness mechanisms, actually, to understand the health status of train components. Because if train should take a decision, it should be aware of everything, both inside and outside. And up to now, for some directions that came out are related to reinforcement learning, which has been, let's say, widely studied in automotive and could be extremely useful in train driving, as we are trying to understand through the virtual coupling case study. But also, we would need advanced train driving simulators. We try to build like a trivial one, let's say, but clearly these driving models, these driving systems cannot be tested directly on the field. So we would need advanced train driving simulators to understand the effectiveness of the systems, at least from a proof of concept level. But afterwards, we would also need clearly to test these on the field. In the meantime, but we can build it. It would be possible to take into account the fact that digital twins can be built to bridge the gap between a simulated environment and the real environment, so that with this direct link, we could like understand how the real environment would evolve in case of some disruptions, malfunctions, etc. So, I mean, with this integration, we could move towards that we can define as proactive safety. So to try to avoid and predict any fault or accident. So next slide. And okay, I think I can give the
Okay,
floor
thank you.
again to
Thank you,
Professor Fermini.
Lorenzo. I think that we can give the floor to Rui Van Tang, who is the other PhD student who is working on the project.
No, Francesco, sorry. Predictive maintenance.
Okay, sorry. This is part that is allocated to myself. Sorry for the misunderstanding. So, okay, this is where about work package number 3. So we are addressing artificial intelligence for predictive maintenance and defect detection. Next slide, please. Okay. In this case, what we want to, in this part of the project, what we want to do is to leverage on artificial intelligence and machine learning to support intelligent maintenance. And the case study that we have selected to this aim is the level crossing case study. Why this is very important case study. It's not the only critical asset in railways, clearly, but we have studied the current reports that say that level crossing accidents account for at least around 30% of all railway fatalities. So this is a very critical railway asset. The objective here is to use non-intrusive sensors in order not to interfere with the current certification of level crossing. So the problems is to address are to provide a system which is not intrusive, and also to leverage on a suitable data set, which is, as I said, the common issue with these AI machine learning applications. So what we wanted to experiment is the use of possibly existing cameras and microphones in order to detect any failures and at the level crossing, and again try to use simulators and approaches based on transfer learning. Next slide, please. Okay, so the basic architecture of a vision-based monitoring system for level crossing is depicted in this slide. We used a common scenario in which you have the level crossing barrier that is opening and closing. Then you have warning signals that are divided into two categories, basically. One is the light signal, and the other one is the acoustic signal. So you have warning lights and warning bells. So what we wanted to achieve was a completely autonomous system. So a system that did not need interfacing with the signaling system or understanding where the train is located. This you can do by watching the status of these three subsystems, so the barrier, the warning light, and the warning bell. In normal situations, the three systems must behave in a way that is coherent. Okay, so when the barrier is opening and or closing, you have a coherent behavior in the warning light and warning bells. Otherwise, if the three subsystems are not behaving in a coherent way, then you have an anomaly. So this is the overall picture of the system, but then at the single subsystem level, so for the barrier, for the warning light, and for the warning bell, we used different techniques based on the deep learning, as Lorenzo will show in the next slide.
Okay, so for this module, clearly the aim is to try to detect the warning bell of the level crossing. And also in this case, we did not find any data set available online containing warning bell audios. So we built one from scratch. And actually, we treated this problem as a three-class classification problem because there are some other alarms that can be recorded next to level crossings that can be confused actually with the level crossing bell sound. So like car horns, car alarms, etc. So to build the dataset from scratch, we leverage the audio set dataset, and also the I say the philosophy that is behind the audio set dataset, which means this dataset contains data that link to audios of YouTube videos. So with the same philosophy, we collected like data related to the three classes you can see here. So warning bell, generic alarm, and no alarms. And we built like let's say a small dataset of 1,197 10 seconds audios. Then we split these 10 seconds audios in one frame audios. In this way, we have 1 second, 1 second audio frames. In this way, we can detect each second if the bell is ringing or not. Next slide, please. So to do that, to implement this module, we leverage the VGGish architecture named exactly VGGish, and that has been developed always in the context of AudioSet. And also the weights of the network were made available by the authors. So we applied transfer learning in this case by taking advantage both of the network and the predetermined weights, and then fine-tuning the network on our dataset. Besides the numerical result, what is more important, according to me in this slide, is the contribution transfer learning has on this specific case study. So normally when training a deep neural network, we will have like a initial phase when the network is characterized by oscillations in the losses you can see on the bottom right. And typically these oscillations should like be smoother as the epochs with advancement of the epochs. But in case we do not apply transfer learning, we can see that the performance of the network diverges instead of decreasing. While when we use transfer learning, the behavior of the network is more stable in this sense and is more smooth. So these results seem to, let's say, validate the theoretical hypothesis that transfer learning could be an extremely interesting and valuable approach when only a limited amount of data is available, as in this case. Next slide, please. And
Lorenzo,
here we have
last 2 or 3 minutes.
Yes. And here we have the other model. This is the barrier analysis model. And try to go very quickly here. We collected some data from a real-life simulator, which is GTA. Then we took advantage of the fact that the camera is fixed, so we can crop out the area related to the barrier to clearly crop out that area, and then we applied some data augmentation to increase the dataset dimensions, or like samplers again, or shadows and so on. Next slide, please. And the let's say the aim of this module is to detect the movement of the barrier and not the barrier itself. So here we see on the video on the bottom left, while the barrier is moving, we can detect the barrier, and we can trace the movement of the barrier by taking into account the height of the bounding boxes over time. The confidence of the model is quite high. It's above 95% from most of the frame. We have only one frame here depicted on the right, where the confidence is quite low. And this is built because probably we are trying to figure it out how, why. This is probably due to this like gravel path we can see here that somehow can fool the network. As I said before, the stability of deep learning network may be fooled by slight variation on the input. But the barrier is detected actually, so it's just a matter of confidence. Next slide, please. And by tracing the height of the bounding boxes over the frames, we can actually obtain the movement of the barrier over time, as you can see on top left chart. And we also try to randomly generating some anomalies like quick drop, swinging drop, or slow drop. And we are currently studying some metrics to understand whether, like, without applying deep learning, we are capable of detecting anomalies in the movement of the barrier. And for example, here we are using time and mean squared error metrics, but we are trying to understand which is the correlation between the actual malfunction and these metrics. So next slide, and I'm quite okay. So just a few remarks. The strengths of these approaches are clearly non-intrusiveness, as let's say mentioned by Professor Farmini before, the adaptability of the motion feature extraction process, as I showed in the case of the barrier analysis module, and technology reusability, because we can actually use cameras already installed at level crossing, even from different angulation, because we are only extracting the height of the barrier to understand whether the level crossing is behaving correctly or not. And as for the next activities, as I said, we are trying to find the correlation between possible metrics and anomaly data, and we will working on the two modules we have not discussed in these slides. And so, okay, so that's we can go next slide, and I think I can leave the floor to Ruifan for the next session, let's say, sub-session.
Yeah, thank you. Thank you, Lorenzo. And hi, everyone. My name is Ruifan Tang from the University of Leeds. My research topic today concerning about the applying AI to trend primary delay prediction from the perspective of different levels of the railway networks, including station and route levels. Next, please. Like other physical or virtual data objectives commonly seen, such as voice, images, or videos, traffic dynamics and the network structural information are always so difficult to be captured, and it's the most difficult part to be incorporated into public transport modeling process. However, it is such important to capture and preserve such kind of complex non-linear correlations and topology dependencies if we want to predict primary delay for train services effectively. Although a handful of the work have considered the spatial and the temporal correlations, there has been no attempt to combine the machine learning method and graph embedding techniques for implementation. Also, it's hard to say a particular algorithm is outperform than another one with the growing amount of the data. So to fill this gap, we innovatively proposed the graph embedding, the structural deep network embedding method framework in this case study. In the meantime, we need to take several challenges into account during modeling. For example, the obtained route embedding must be uniformed on the size, and the essential information of this structure must be preserved despite of the length or various stations the service servings. In addition, showing as a bar chart on the right bottom side, several delay cases are not that easy to be acquired due to the practical scenarios, which means we probably won't get sufficient delay instances for training purpose on some specific delay categories. Next, please. And this to the aim of this, we basically divided the task into 4 steps. The first one is to develop and fine-tune the proposed SDNE model, and then assess the feasibility of applying such node embedding method to interpret railway station characteristics, and based on which we suggested finding an alternative way to transform the generated node embedding representations into a route embedding. After obtaining the route embedding, we incorporated them into machine learning-based delay prediction models with other available features. Next, please. In the framework of SDNE, we fed the original network characteristics, such as the adjacency matrix, link weights, as well as other network topology indicators into the encoder and decoder framework, where it checks the connectivity and the structural significance between each pair of the station. It also assigns with first order and second order proximity, respectively, with the objective of minimizing both global and local structural preservation costs, such that a smaller sized node embedding can for each station in this network can be trained and optimized round by round. And finally, we got the compressed station representations without any information losses. Next, please. The SDNE model is only able to generate the node embedding. However, the key issue for the further consideration is to do the route embedding, as I said before, since it can be used to represent the route features for each train, which is highly important in characterizing the train services itself. So simply concatenating node vectors are not that reasonable in this case. So we need to model the network topology specifically from by using another innovative method called the singular value decomposition. This is a powerful tool for extracting matrix information, and SVD also perform the matrix decomposition by extracting the most essential information, which we call the singular values in the original vector. In this study, we performed the SVD strategy on generated node embedding vectors and use the singular value to represent the route embedding vectors, such that the route length of different train services can be normalized, and the dimensions of the original network features can be reduced significantly. And here we give the 4 different examples for different routes in the investigated network. Route 1 is the route information from one of the station running by Transpennine railway undertaking in UK, Newcastle. And the route 2 is another service, a little different from, but very similar to route 1, with 1 extra serving station. Route 3 is a subset of route 1, and all the calling station in Route 3 exist in Route 1. However, it doesn't stop at some intermediate stations. And the Route 4 is a service that's totally different from the Route 1. So it belongs to another area. Next, please. So the figure above on the left depicts the location of these 4 routes representations in the Euclidean space. As we can see, the embedding of route 1 and 3 are projected very close in the embedding space, but followed by the route 2 demonstrate the very similar pattern in this embedding space. And it's a relatively short Euclidean distance from route 1. As we analyzed before. And by contrast, route 4 is embedding remotely from all of the routes above. For the best performed multi-layer perception classifier, which is best performed trend delay prediction model, the prediction accuracy on each of the subcategory in the best performed model, especially on the non-delay cases and the serious delay cases, are already achieved a relative high value. But different classes demonstrate different capacities on particular delay level. For example, apart from the mild delay, multi-layer perception maybe is consistently outperformed than other 2 competitive classified the benchmarks. Another trend we can find is the multi-layer, the more complex and well-constructed models are more reliable on the data set, on the target data sets. They are promising to achieve a more stable prediction accuracy at their end, which means our proposed SDNE plus SVD model may have the more robustness regarding different kinds of data sets. The
Sorry,
graph on,
Stefan, you
yeah.
should close.
Yes, sure. Yeah, this is basically I want to present today. Yeah, next hand to the Francesco for ending. Thank you. Yeah.
Thank you, Ruifan. So now we are moving towards the last phase of the project, which is the definition of the roadmaps, which will happen in the first half of the next year. Just to make a summary of what we have done so far, we have worked quite a lot on the definition of the state of the art through literature review, industrial surveys, analysis of the regulatory landscape, current projects, and this has been I would say key content of the deliverables of the project in the first part of the project, especially. Now we are towards the end of the analysis of the case studies that we have defined for this project. So we will summarize the lessons learned from the study of these specific applications that have been described in this presentation by especially by Lorenz and Ruifan. And in the meantime, after the project started, actually, there were other roadmaps from other domains that we will take into account to define the specific roadmaps, which is the main output of this project. And we also want to involve again the relevant railway stakeholders to ask them for their predictions, informed opinion and judgment about the future of AI in railways. Next slide, please. Okay, I have mentioned these other roadmaps that exist, and they are very recent. For instance, there is one from European Union Aviation Safety Agency, EASA, dated 2020, which is named Artificial Intelligence Roadmap, Human-Centric Approach to AI in Aviation. And then there is another report from Senelec, which is very important for us to take into account, which is the roadmap on artificial intelligence. So this happened while we were working on the project, and of course we took into account this input, and we will continue to take into account this input. We have had also a couple of meetings with the Senelec working group. So next slide, please. So in the roadmaps, basically we will address the most relevant research and development directions, and these will be divided into short-term expectations and long-term expectation from AI technologies that can be applied to railways. We will focus on the scope of the rails project, so there will be possibly other domains that subdomains within railways that we are not addressing in the project. That we will not that will not be our specific focus in the roadmaps, and we will point out methodological and technological aspects. So there will be two aspects. One is more about the methods, and one other is more about available technologies and enabling technologies. Next slide, please. So I said that next step is to define these roadmaps, and we want to involve again the railway stakeholders. So we plan to have an event, a dedicated event in spring that will be fully online or possibly hybrid. And one objective is to share the results, current results with the stakeholders, and the other objective is to collect indications from them. So we are currently organizing the event, and there is the possibility for you to subscribe through a Google form. So if you want to be informed and receive updates about the event, please fill in this form that we have prepared. I think it's next slide, please. We have finished with this presentation. Thank you for your attention. And we will be happy to answer any questions.
Thank you, Francesco. Thank you, everyone. So indeed, now there is a chance to ask questions. So the participants, the guests can ask questions using the chat function that you find in Teams. So please go ahead. Okay, while we wait for the questions, maybe I can ask some questions. So concerning the autonomous driving obstacle detection. So in the context of vision-based obstacle detection, why did you need to realize a simulated scenario? If you could explain.
Okay, yes. Thank you for the question, first of all. So the need comes from the fact that, for example, the data set that is available online, which is a Rails M19, does contain different pictures of railway lines, but it lacks in what we can call domain-specific characteristics. So if by building a simulator, we can collect data coming always from the same track as to exploit like task-specific characteristics, which clearly are related to always to the same railway track, and limit the aleatory of the environment to only weather conditions or possible intrusions, but not to structural differences. Clearly, this can be also done in real life by collecting data always from the same railway track, but then it would be quite complicated or unsafe to put obstacles on the rail track and let train running there to collect data. So just a quick example to explain better this is in the context of, for example, rails detection. If we train the model with all the frames collected from the same railway track, considering, for example, also different weather condition, etc., when the model will be run at runtime, it will probably see a scene that which has probably already seen during the training phase. So the result would be more or less better because we are kind of reducing the aleatory due to the structure of the environment. That's the main reason.
Okay, and concerning the level crossing, so there the question would be how you generate the anomaly data for the barrier, and also can you detect that the barrier remains open or it's malfunctioning? Is the system able to detect some this kind of cases?
Okay, so as for the generation of the anomaly data from the real-life simulator, we only got perfect movements. So we have only let's say nominal behavior of the barrier. But by applying some randomness in these like path, we can simulate very different, I mean, like simply algorithms, we can simulate various movements of the barrier. Clearly, they should be close to the reality. So we cannot have a movement that is not, let's say, recordable in real life. So we are also trying to figure it out how to implement this function if possible. And as for the second question, actually, let's say that the anomaly, the barrier analysis module will focus on detecting mostly defects that are similar to those I showed you in the slide before, like quick drop, swinging drop, or slow drop. But for other anomalies, like the barrier never closes, or as you mentioned, or the barrier never opens, actually, that could happen. We could see the system as a triple modal redundancy. Please let me use this parallelism, because if the bell start ringing and the lights start blinking, but the barrier does not close, this means that we have a malfunction in the barrier, most likely. And same goes also if the barrier never opens when the other two warning signals have stopped functioning. So that's I guess I hope I've answered your question.
Okay, thank you very much. I will just check in case there is a question from the audience in the chat. And otherwise, also in the interest of the time, I believe we need to close here this part, and we will continue then with the next presentation. So we will continue with the research on blockchain, which is done within the B4CM project. John Easton is the coordinator of the B4CM project. He's an associate professor at the University of Birmingham. John, welcome, and the floor is yours, please.
Thank you so much. So good afternoon, almost good evening, everybody. Thank you for making the time to come and listen to this today. So as Gozat has told you, I am John Easton, and I am here on behalf of the B4CM project. So B4CM project is looking at how we can use blockchains to help us understand condition monitoring data. So B4CM itself was a very small scale project. It was a partnership between a micro enterprise called Iconic Blockchain. So they are a company that is basically very interested in blockchain technology and how you can exploit that in different industries, and ourselves at the University of Birmingham. So in the scope of the project, what Iconic were here to do was to provide initially, early on in the project, a bit of a steer as to how these technologies were currently being deployed industrially, and also do a bit of scene setting and to do some document reviews. And then from the university side, we provided basically a PhD student who did the majority of the work that's been done on the project. So a big shout out to Rama Al-Zarani, who did most of the work that you see here today. So what we were looking to do within the project is we were looking to quantify the flow of RCM data between stakeholders. And I'll get to what I mean by that in detail in a moment. There were, of course, a collection of specific objectives that we went through as part of the project. First and foremost amongst those was this idea that we needed to develop a framework for the attribution of condition monitoring data costs across organizational boundaries. So we wanted to understand that data flow. We wanted to then look at different mechanisms that we could use to incorporate a cost with those data flows. So we wanted to not only understand the data flows, but we wanted to be able to remunerate organizations for the data that they were providing, or have them, compensate the data producers for data they were drawing out. And we wanted to develop a test bed or a demonstrator that would support future development in this area. Alongside all of that, we also wanted to do a bit slightly more general piece around the identification of other use cases for blockchains in rail. Like most industries, there are quite a few use cases where this technology could apply. So various obvious examples are things like ticketing, but actually also you have, for example, less obvious cases, condition monitoring one, which we were investigating within this study. You could also think about using these technologies to, for example, provide an audit trail where you were looking at things like automated driving, which links a bit back to the presentations that we've just been watching. Next slide, please. So first of all, why do we need something like the framework that B4CM was proposing? Well, first of all, of course, it won't be as a surprise to any of us here to read that rail is a complex environment. It's a multi-stakeholder industry. The image on the right there, which I'm afraid is slightly aliased, apologies for that, is a simplified version of the structure of the industry here in the UK. There are quite a few arrows removed actually to make it a little bit more readable. But we can see here that we have a lot of different actors going on within our railway. We have Network Rail, who are, of course, the infrastructure manager here. They're providing access to the track via mechanisms that are paid for by various operators, so the passenger train operators and also the freight operators. But then those operators themselves are also having to lease their vehicles, for example, from the rolling stock companies. There are supply chain entities, and all of this is being overseen and supervised by the DfT and ultimately by the Treasury. Now, when we think about condition monitoring, we tend to think about condition monitoring within the scope of one of these sets of actors. So, for example, we might think about Network Rail installing some condition monitoring on some points machines that allows them to understand the condition of that asset, and providing, constructing a business case for that type of system where you've got a system that is owned and operated by the same actor is comparably straightforward. But when you start to think about systems that maybe cross those organizational boundaries, things start to get really quite complex. So if you think about, for example, track monitoring equipment that is installed on a vehicle which is being operated in passenger service by one of the train operating companies, well, straight away you can start to see some complexity, because the train operating companies are already paying Network Rail for access to the track. So if by carrying that extra equipment, they're generating some fill-in data between inspection runs of the network inspection trains, which is of value to Network Rail, then suddenly you start getting this very complex environment where there's a lot of cost being borne by one of the entities, in this case the train operator, but all the benefit is being felt by the other. It's being felt by Network Rail. And it was these sorts of interactions that we were looking at with a view to providing an audit for those data transfers, and ultimately to be able to support things like novel business cases for this type of system, which basically provided a benefit to the industry, but that benefit was quite hard to quantify and quite hard to account for. There have been various pieces of work in this area around delivering business cases in a traditional sense for this type of equipment. There was some very good work done, for example, by RSSB and their cross-industry remote condition monitoring workstream, which provided template agreements that allowed companies to begin to essentially put agreements in place for systems where data was being used in a fairly static context. So if you knew that there was only ever going to be one set of customers for your data, and you knew that system was going to be installed for a long time, how could you go about creating a traditional contractual relationship for this? But that maybe doesn't have the flexibility that perhaps we might want going forward. And what an alternative solution would be to basically provide a mechanism whereby we could have a trusted audit of those data exchanges that were going on within the system. That really would help us understand which entities were contributing data and where that data was ending up, what the benefit was and to whom, and essentially amounts to a value chain for our condition monitoring data. So that was the area of the industry that we were really aiming to investigate. Next slide, please. So for those of you who are unfamiliar with the technology, up there on the right, we have our blockchain. I'm kidding, of course. This is actually a piece of marble at a quarry in north of Italy. But there are lots of people out there who, when you say blockchain, they may be familiar with the term, but they perhaps don't understand what that actually means. So a blockchain, in many cases, people will think of, when they hear blockchain, they will think of Bitcoin. And yes, Bitcoin is a blockchain, but not all blockchains are cryptocurrencies. Okay, there are lots of other uses for blockchains, although the technology did basically develop out of the cryptocurrency field. So at their heart, what blockchains are is a distributed ledger. So they're a record of the transactions, of a set of transactions that have happened involving a particular asset. Now, what makes the blockchain different is that that ledger is then shared across a number of different platforms operated by a number of different users and agreed upon. So there are lots of different copies of that ledger, and all those copies should agree with each other. Facilitating that, we have a particular data structure. So we have a chain of blocks of records. So imagine a traditional transaction log. So you generate a set of transactions. Let's assume that you're generating sets of 20 transactions. You're going to take those transactions and you're going to bundle them up into a single entity, which we're going to call a block as part of our blockchain. Onto that block, you're also going to include a record of what the block that was before it on the chain looks like, and you're going to attach your new block to the chain. And as you do that, as you build up your record, you find that you have in the middle of your chain, in each block, you have copies of what the data in the block before looked like. And that means that your chain, once it's got 2 or 3 extra blocks added onto the end of the block that you've just added, is going to be tamper-proof, because you're not going to be able to change that record of what the chain looked like previously without going back and regenerating everything. So you're going to have an awful lot of computational effort to be able to replace one of those blocks, and that means that that record is then tamper-proof. Next slide, please. So why does this matter? Why can't you do this with traditional ledger technologies? Well, of course you can. But the advantage of the blockchain is that it's got this distributed network around it. So what that means is that no one entity is in charge of that ledger. And that means there is a reduced requirement, if you like, for trust in a single entity within the blockchain. And that makes it perfect for audit. It does create a few problems. It means you have to decide which transactions are legitimate when you add them to the chain and who can add those blocks to the blockchain. And there's a mechanism for this within the technology, a thing called a consensus algorithm, which basically allows you to create an agreement amongst the partners within the network that a block is valid. How you go about doing that is quite complicated. It usually relies on some sort of cryptographic sum, if you like. And actually, that was one of the big penalties of using blockchains until quite recently. They were really very energy intensive. One of the things that we've just been seeing in the news this week is that one of the big blockchain platforms, a chain called Ethereum, is swapping from an old consensus mechanism, a thing called proof of work, to a much more energy efficient version, thing called proof of stake. And I understand that energy is one of the themes of today. So that's really important. The new generation of these technologies are much more energy efficient than the previous ones. Next slide, please. So it turns out that blockchain platforms are rather like buses. So you wait for a long time, and then loads of them come along at once. And blockchain is one of those areas where we've seen very rapid growth in the last 5 years or so. There was a paper that came out September last year that reckoned there was roughly 25 or so major blockchain platforms that were currently being used. And obviously, we're going to need to be able to choose between those to select the basis for our framework. One of the things that we needed to consider here was that the traditional use cases, so cryptocurrencies, the requirements of those use cases really differ quite heavily from more general ledger application use cases, which is what we're thinking about here within B4CM. So that helped us narrow the field substantively. But then Rama had to go away, and within the set of platforms that she had left, she had to choose between them. And the way she did that is she looked at a whole load of different requirements we had for those chains. So she began by thinking about the difference between public and permission chains. Now, cryptocurrencies tend to use public chains, so anybody can contribute, but because we're working in an industrial context, we're going to need some measure of identity and identity management within what we're doing. And that is going to mean that we can make use of a permission chain. So that's going to give us a certain number of benefits there. She also wanted to think about business logic. So one of the things that we want to do with our chain is not just record transactions, but we also want to be able to do some business logic across those transactions. So, for example, what are the requirements for exchanging particular items of data? And we can do that within a blockchain environment using something called a smart contract. So we were able to narrow down that field based on the chains that were capable of supporting smart contracts and essentially automated transaction management. We wanted to be able to look at the possibility of using different consensus algorithms. So we've again narrowed it based on that. And also we wanted to be able to use a platform that didn't require its own in-platform currency. And that's quite important because a lot of the platforms that were developed out of cryptocurrencies, they made use of their own internal currency models. We didn't really want to be doing that. We wanted to be able to use essentially normal currencies if we did, so fiat currencies. So all of that brought us down to using the Hyperledger Fabric platform for the blockchain. Next slide, please. So from that point, Ram was able to go away and she was able to look at the different architectures that she might want to use. She's settled on something that is really quite familiar to anybody who works in a sort of a web-based development environment. So we have our blockchain, which is hosted on our Fabric platform, and that blockchain has nodes which could be spread across a network. In the case of the demonstrators we've done for the project, of course, they're all hosted on one machine, but the platform is capable of supporting a chain which is spread across multiple servers in multiple organizations. So the idea is that each organization which is involved in the blockchain will host one or more of those blockchain nodes, and the collection of those nodes forms our network. The network has the copies of the ledger spread across it. So each organization involved in the network is going to have a copy of our ledger. On the front of that blockchain, we then have a set of APIs, and that allows us to create interfaces to the blockchain. In Ram's example, what she's done is she's created a JavaScript-based set of interfaces. So she's used Node.js to provide some web-based APIs that she's then connecting to using Angular. She has a local database for managing that client application, so she's using MongoDB for that. And then, of course, the users are connecting straight to that interface. One of the important things to say here is that the data storage is going on off-chain. So on the blockchain, we're recording the transactions, but we're not actually holding the data that's been exchanged on the blockchain. And why we're doing that is quite important, and we'll get to it in a second. Next slide, please. This is basically showing you the same information from a slightly different perspective. So what Rama has done in her implementation is she's used Hyperledger Fabric as her ledger, and within that she's using CouchDB for the world state. And you use CouchDB in this context because it gives you a capability for a rich search of the transactions on your blockchain. All of that is then encapsulated in Docker containers to make it relatively easy to spin up instances, keeping in mind that this needs to be ideally hosted in multiple places. So you need to be able to set up servers in lots of different locales. And then we have the Node.js API server and the Angular front end that I've already spoken about. Next slide, please. Okay, so data in real time. So this is one of those aspects I was touching on just. So one of the big problems with blockchains in terms of managing data exchange is that the blocks on the blockchains that I already said are basically protected, if you like, using cryptographic processes. And what that means is you're going to need to do some calculations over the top of the blocks and over the top of the chain to be able to add new blocks. Now, if you add a lot of data into your blocks, that gives you a problem because that cryptographic maths is quite intensive. And if you've got a lot of data that you're trying to do it across the top of, then that's going to mean that your performance is going to be very poor. So if you want a real time, if you like, performance out of your blockchain, then what you're going to have to do is store the majority of the data off chain and then just store the information necessary to evidence who has who has exchanged the data and who has the right to access the data on the chain. Now, that might not be a problem if all we were interested in terms of our data exchange was data about specific events, because data about specific events might be quite small. But actually, in condition monitoring, we tend to be thinking about one of two types of data. Either we're thinking about data related to specific events, and that is what we tend to be thinking about when we're talking about runtime, if you like, when we think about a system as deployed. But particularly when you're thinking about training a new system, then actually what you're interested in is historical data. You're interested in a large corpus of data that represents that system over an extended period of time. And that means we're going to have to be using off-chain storage. Fortunately, our distributed ledger technology relies on signatures to identify the actors within the system, and that we can leverage those to facilitate secure access off-chain. So within our blockchain-based process, what we can do is we can arrange for the exchange of data. We know who we're exchanging that data with because we already have their signature. So we can use that signature to protect the data that's off-chain, which makes sure that only that individual can then access that data effectively. Next slide, please. So here is an example of the transaction flows that Rama has developed as part of this process. So this is a provider-side transaction flow for a data exchange process going on within the system. It looks quite complicated, but actually there's only a very small number of core functions that are going on in here. It's just it's split up in a way that makes the processing sensible. So fundamentally, what's going on in here is we have a provider who is creating offers of data, so adverts of data that are available for exchange within the system. We then have on the other side of this, if you like, a client making requests against those data offers, so responding, if you like, to the offers of data. You then have some sort of process around the transaction itself, so that might be a micropayment transaction or it might be an escrow process, and Ram's quite interested in the escrow processes, and we'll get to that in a moment. And then potentially you might have some sort of resolution process to tidy up any loose ends associated with the transaction. Next slide, please. Here's one example of that accounting model. So this is the escrow process I was talking about just now. Now, the reason that Rama was interested in the escrow processes is she'd been thinking about these two different types of transactions. So the transaction around the small data item, the event data, as I said, you could handle with a micropayment model, and that could be automated very easily and would create a streamlined workflow and would be an unattended process, which is ideal. But if you're talking about larger data sets, so these historic data sets that you might need for training, for example, the value of those data sets might be very significant, and you probably need some sort of protection from things like fraud around that on the part of the provider or on the part of the consumer. So things like late delivery of data, incomplete data, or perhaps something that's resulted in a change of commercial circumstances while the agreement to exchange the data is in force. So maybe a data provider losing the right to ownership of the data that they're offering for sale. And in those circumstances, you need a mechanism for either the provider or the consumer on the other end of the transaction to be able to essentially say, no, this is not what was agreed, and invalidate that agreement. So that's why this escrow process is in there. There's quite a lot of scenarios around which you might want to use this process, and she's detailed all of those in deliverable 2 of the project. So if this is something that's of interest, please do go and look at that deliverable 2. Next slide, please. Obviously, we've produced a demonstrator which lets you try this stuff out. So in the final demonstrator for the project, we're looking at a scenario around in-service monitoring of third rail. So that is kind of like the scenario I was talking about at the top of the presentation, actually. So where you have some equipment on an in-service passenger train, in this case, looking at the shoe gear, which is monitoring the condition of the third rail, the power pickup rail, alongside the train. That data is obviously of use to the infrastructure manager. It's of use to maintenance companies, but all the cost is being borne by the operator and by the ROSCO for the installation and upkeep of the equipment and the access they're paying for to the track. Within that scenario, we've created a network which is running 5 different organizations. There's a couple of TOC organizations running within that network, an infrastructure manager, maintainer, and a ROSCO, and each of those has 2 peers running within our network, so they have 2 copies, if you like, of the ledger running within the network. All of that stuff is going to be available very shortly on the project's GitHub, which you can see the link for at the bottom of the slide there. At the moment, the version that's on there is a slightly earlier version. It's the version that we released just after deliverable 2. Please do feel free to take a look at that version too, but actually it's quite fiddly to install, and the new one is going to be much easier to install. So I suggest giving it a couple of weeks and then taking a look when the easier to manage version is up there. Next slide, please. So we're right at the end of the project for B4CM, but what do we want to do with the ideas going forward? Well, one of the things we're quite interested in is whether any of this is going to translate well to higher technology readiness levels, basically whether or not it's able to be developed further. That is something that obviously as a university we're not that well suited to ourselves, so we're going to be talking to some of the supply chain companies about how we might take those ideas forward. We also do quite a lot of other work in the blockchain space. So we have, for example, a project which is just setting off, which is funded under a different European stream. It's funded under Trublo. It's a project called Stub, and that is looking at how we can use blockchains for ticketing within rail. Next slide, please. Where can you go if you want to find out more about the project? Obviously, there are publications. I'm academic. We always love publications. So there's a publication in the 2020 IEEE conference on big data, and that essentially reports on the framework delivery within the project. There's a journal publication in the Journal of the British Blockchain Association, which is reporting more on the commercial processes that Rama's been looking at. All of that is available along with the deliverable documents on the project web pages. So that's at b4cm.co.uk. I really apologize for that not being a .eu address. It wasn't my choice. And also there is a Twitter handle for the project, although that is relatively quiet. I'm not a great user of Twitter, it would have to be said. Right, next slide, please. Okay, we're there. Does anybody have any questions?
Thank you, John. Very comprehensive presentation. I'm looking now at the audience in case there's some questions coming up in the chat window. Now is the opportunity, please. Okay, while we wait, maybe I can ask some questions if you don't mind. There have been lots of attempts at using blockchain-based systems in the industry. Most of them haven't worked. Why do you think this could work now in rail?
Yeah, so this is a really good question. It's one I get asked quite a lot, actually. Blockchains have been treated rather like a child with a hammer by academics and industry in general. So if you give a child a hammer, the child will attempt to use the hammer to do basically every job that he sees in front of him. And quite obviously the hammer is well suited to banging in nails, but it's not great for doing the washing up. And that's kind of what's happened with blockchain. Lots of people have gone away and they've explored lots of different application areas for blockchain, and that I think has created a certain reluctance, perhaps, on the part, particularly of big industry, to adopt the technology, just because the application areas where people have been trying the technology haven't been right in the first place. They were never going to work, and therefore the projects have failed. Now, one of the key things to the technology then is understanding really where a blockchain is the right answer and where it's the wrong answer. Now, in this case, blockchains are a good answer, and the reason for that is kind of tied to three different features of the technology that you need to be considering. So, first of all, what is the spread of the participants in the project you're trying to solve? So, how many people need to have access to your ledger? And how many of them need to be able to write to that ledger? And the combination of those things says, well, does your ledger need to be widely available? In which case, does it probably need to be distributed? And also, do you have a sort of a trusted environment in which only one person is writing to your ledger, in which case you probably don't need a blockchain at all? Or do you have lots of people writing to your ledger, in which case you need a sanity check across the top of that to make sure none of them are behaving fraudulently, essentially? Then there's a sort of a data angle to it. So how confidential is the data? What sort of scale is the data at? And how important is the provenance? So how much do you need to understand about where the data has come from? And obviously providing audit trails allows you to make use of all of that. And finally, what's the sort of the performance requirement? So if you need very, very fast performance, you probably don't want this type of technology at all. You want a standalone solution. If you can cope with very, very slow performance, as long as you've got a trustworthy ledger, then you can use a public blockchain. Or if you're somewhere in the middle, which is where we are for this sort of application, where you have an understanding of what the identity of the people using the network is, then you can use a permission blockchain, which gives you a sort of a good balance between those two states.
Thanks. We have a question from the audience. So I will just read it aloud. Do you think that BC, so blockchain technology, may support data sets sharing among different railway players to build a data center for artificial intelligence applications in the respect of different access rules and rights? I think that's an interesting one.
I absolutely, yes. So I definitely do think that could be the case. The whole question about data marketplaces in rail is really interesting at the moment. So I know that, for example, here in the UK, the Rail Data Council, which is primarily led by the Rail Delivery Group and various other people who are traditional industry actors, are talking about how we go about creating data marketplaces within rail. There are various different ways of doing that. One of which certainly would be a blockchain-based solution, albeit that data, as I was saying, with same situation that we have with the condition monitoring data. You would need to have that data off-chain, so you would need to have some persistent databases which you then referenced from your transactions on the chain. But yes, that is very much an open opportunity, I think.
Valeria, thank you for the question. So others from the audience, if you have questions, we still have a few minutes before we start the next session. Otherwise, I can try another one. So, John, surely there are other governance processes or commercial agreements that could achieve the same or similar outcome. What advantage does this approach bring?
Yeah, I absolutely. So there definitely are. So I mentioned earlier on in the presentation that for example, RSSB, so as part of their cross-industry condition monitoring workstream, they've created a set of template business agreements which allow you to create a contract whereby you've got the various actors involved in a condition monitoring system paying at least something that approximates to a fair amount of money for the collection costs and the maintenance costs of the equipment, and then get a fair share of the benefit for that data is generating in a fairly static sense. So the problem with that approach is if you want your data to, for example, be accessed in a fairly dynamic way by lots of different stakeholders, then actually suddenly there's a lot of different benefits and you'd be having to continuously update those commercial agreements, which is quite a complicated job, as it turns out. And that's where the benefit from the blockchain type solutions really comes in. So by building the ledger, you have your audit trail for where your data is coming in, and that data source could be appearing only for a very short period of time. It could be an IoT type solution. It could be, I don't know, ride quality measurements from a passenger's cell phone or something like that. That you've got on a coach potentially. I don't think you'd ever want to be including data of that level of quality in a system, but you can see where I'm going. There could be a lot of sensors that are contributing quite dynamically to the environment. And in the same way, you could have people who are trying to develop new solutions for track maintenance and things like that, who are drawing on that data to test their own products and might only be drawing on it for a very short time, and who you wouldn't want to set up a formal commercial agreement with, but you understand what the contributions and the drawdowns of the data are because you have the ledger, and then you can go back and essentially account for those transfers and monetize them.
Okay, thank you very much. If there's no other questions now from the audience, we can move also to the next session. So thank you very much, John, for your presentation. And now we are at the last topic for the day, where we will look at the work done by Project Tauro, which is related to system architecture. The presenter is Bastien Simoni from Alstom. He's a mainland signaling system architect. And please continue.
Thank you. Hello, everyone. So we are going to speak about the work that has been done within Tauro, and it's still ongoing up until next year regarding the line stack signaling interpretation. And so the first question that we will ask ourselves is why to get the signal aspects visually. So what we have here is the figure of the system architecture of ATO, so automatic train operation for JOA2 that has been defined within the Shift-to-Rail project and will be within the next TSI CCS for the ATO use case. We can see that we have the ATO on board in the box in the box here with the subset 125, and the ATO trackside, which is connected to the legacy systems or new systems, traffic management systems, to get the timetable. So this is for the ATO part. And you see that we also have the ETCS part, of course, in orange, with the ETCS on board, necessary to fulfill the use case to get the signaling information, and also the ETCS trackside part to get trackside information for the ETCS on board. And the challenge we have is that, of course, this use case is possible for lines that are already fitted with ETCS trackside. So now, if we imagine that we leave an area, an ETCS area for an area with a Class B system or legacy system, then there is no more ETCS trackside in the scheme, and the ETCS on board switches to the level NTC, so the National Train Control level, that is then under the supervision of the Class B system, the legacy system. And in this level, it is not possible to have the ATO on board active, so it is not available. And so the whole use case of automatic driving in GOA 2 today and possibly tomorrow in GOA 4 will not be possible on lines that are not yet equipped with ETCS. And this is the reason why in Tauro we are investigating for migration solution. So next slide, please. We want to enable the use of ATO on lines that are not yet equipped with the ERTMS system. Because today, as you know, we are facing some challenges in the highway sector and moreover the whole industry with the rising energy prices context. So energy efficiency is a must. The use of automatic driving, even in GOA 2, can provide energy savings. It provides also a comfort function for the driver and a better respect of the timetable. So for the user's perspective, highway undertakings, the use of ATO over TCS is very interesting. And now, if on the infrastructure side, even though there are plans to roll out ETCS massively, it will take time. So we will have all the time and for the next years, lines that are not equipped and on which today the use case is not possible. So we are investigating for migration solution that we consider as necessary to make the adoption of the ATO over ETCS solution quick and massive and without any modification. We will see this afterwards. And so the perception of the existing line-side signaling and the interpretation of these signals to get the possibility to use the ATO over ETCS solution is one of these possible migration solutions. Next slide, please. So now let's have a look at the complete architecture. So it is maybe a little complex, but I will explain. That is currently built within the X2Rail4 project in IP2. So regarding the ATO up to JWay4, mainline ATO, and in this global architecture, the working group is trying to propose a standard architecture with standard interfaces to bring the ATO up to JOA4 on the mainline infrastructure. So we have on this scheme a blue box that is the complete logical system under consideration in the working group, and you can find the actors in blue around this logical system, like, for example, all the actors related to the infrastructure manager at the top, the highway undertaking also at the top, entity in charge of maintenance at the right, the train preparation staff, light signals that we will discuss, physical environment, and then at the bottom of the scheme, you have the driver, the onboard staff, adapters if needed, and of course the train, the TCMS, the train control and monitoring system of the train that we will connect to. And then if we go back to the logical system, the blue box, you will find in green in the top of the box all the signaling and infrastructure elements trackside with, of course, the TMS, the traffic management of the infrastructure, where you will find the different timetables and the operating scheme. You will find also the route control, so the interlocking part of infrastructure, and the train control, so the trackside part of ERTMS ETCS. You will find also the train management we are on the RU side, which is the system that will manage the operations of autonomous trains on a RU perspective. So how to operate and how to assign tasks and missions, because we will speak about missions in GOA4, a sum of tasks to be executed automatically. And then you have different boxes to adapt the communication with the trackside elements and the onboard. So you will find the DM, the digital map, well, you will find a lot of properties of the infrastructure, the static elements. You will find the OS box, operating scheme, that is linked to the traffic management. So it is a kind of gateway to connect to existing traffic management system and to get the timetables that have to be respected. And then you have MD and TD, respectively for mission data and train data that are the elements coming from the railway undertaking. So these are especially gateways and adapters, so to say, with the existing elements of the trackside. And then with the REP box, REP stands for repository, starts the world of the onboard part of the autonomous train as currently specified and conceived today. Repository is the key element to ensure the interoperability between the onboard and the trackside, to get the mission data, to get the operating scheme, to respect on the track plan, and all the data associated to the need of performing ATO up to GOA4, thanks to the digital map that is located trackside. Repository, of course, will serve a certain amount of subsystems, onboard subsystems. The first of all will be the ATO AV, so ATO Autonomous Vehicle, which is kind of the same of ATO GOA2 as defined today, to perform automatically traction and braking, so to respect the timetable and to optimize consumption. And then you will find new modules to fulfill the use case in GOA4. The first one being the APM, Automatic Processing Module, which is some kind of the brain of the system to perform functions that are done today by the driver. For example, to react in case of an incident, and then to react in case of an incident needs a perception of the physical environment. And this is why we find the perception building block also in yellow, to perceive what is happening in the physical environment, either with cameras, sensors, microphones, and so on. And to fulfill this use case, we need to know where we are on the track plan. This is why we have also the localization building block in the architecture. Localization, which is able to fulfill new needs introduced by ATO up to GOA4, but also to fulfill the use case of ERTMS on board. So this is the box train protection. As you may know, there are projects to sort out localization of train protection and to have a standalone odometry system. This is why we have the localization here on the scheme. The last box I want to talk about in this architecture, and this is the box on which we will focus, is the SCV. So SCV stands for Signaling Converter, which is a box linked with the perception. And perception perceives the object light signal that you can see in the architecture. And SCV is connected to the train protection. And in fact, this is the architectural response and the technical solution to enable the use case of ATO on areas that are not yet equipped with ERTMS, because we convert the aspect of signals that are perceived with PER, and we provide the conversion into the ETCS format, then forwarded to train protection. Next slide, please. And so what are we talking about? In the end, we talk about the interpretation of existing line side signaling. The hypothesis as of today was to say we have in the subset 026 world, so the specification related to ERTMS, ETCS, a certain amount of devices, trackside, balises, Euroloops, radio block centers, or radio infill units that are able to provide ETCS from the trackside to the onboard with the signaling information. And as a co-product, we can have the ATO in gray, so for the GAWA2, and up to GAWA4 with new elements that are defined in X2L4 project, and these elements are in violet. Next slide, please. And what we do in the Tauro project is to define new building blocks, perception and signaling converter to feed a new evolution of ETCS on board so that it is possible to have the ATO over ETCS and the ATO up to GAWA4 use case, thanks to these new means of transmission in blue that you have in the slide. Next slide, please. So now, how do we do this? And this is what we will discuss right now. Next slide, please. Let's take some history and how it is done today, especially in level 1. So ERTMS ETCS level 1 is a semi-punctual implementation of ERTMS as overlay with the existing line-side signaling system. And so in this picture coming from Mermec, you can see how the flow of information starts from the track side, from existing systems, and flows up until the screen, the DMI, the driver machine interface in the cabin. And so there are multiple ways to acquire the information. They are acquired with coders, LEUs, line-side electronic units, that you can have either at the signal or either at the interlocking if the interlocking is capable of. And so, of course, we connect our coders to the existing track side, and these coders are able to provide a neurobalise with the associated ETCS messages thanks to the connection with the existing system. And the onboard fetches with the antenna at the passing of the Eurobalise the standard information that is treated by the onboard EVC, so the European Vital Computer, and then displayed to the driver with the screen. This is current ETCS level 1 implementation strategy. Of course, it is possible to have ATO over ETCS on a line equipped with ETCS level 1, as we can see here. This is how it is done today. And in the group, we asked ourselves how we can possibly have some kind of equivalence with ETCS level 1 thanks to new technological approaches. And so, of course, the level 1 and the specification were written 20 years ago in the 90s, and now how is it possible to reconsider ETCS level 1 with the new technologies? The first element is the progress that has been made on onboard localization devices. Maybe you are aware of projects, investigation programs like the CLUG project in Europe that suggest that it is possible to get safe information with the onboard localization devices with satellite-based technologies, EMUs or telecom solutions, and limited relocation balises on the track. None, we are not there yet, but limited relocation balises, this could be possible. This is the first element. The second element is the progress regarding the computer vision. So the acquisition of physical environment and the extraction of information from the physical environment thanks to computer vision. And here the idea is to extract the aspect that is displayed from the signal as compared to the current method today. And if I'm thinking about France, for example, we use eddy current sensors to get the signal state directly on the wires. So this is another approach. And there are also the concepts explored also in Tauro project, but in other working groups regarding the digital map, where you can find a certain amount of information regarding the network, the track plan data with different perspectives. And these different perspectives within the digital map are able to serve the use cases of ATO, of localization, maybe of perception. We will see this in the next slides, and so on. And the digital map is also something that we are investigating in Toro. So when we say this, these three breakthroughs are able to reconsider the way we deploy ERTMS level 1 today. And so first step, this is exactly the same as today. According to us, we start, of course, with the line study and the application engineering, because we deploy virtually, but we deploy ETCS level 1 on the track side. So we need to perform the line study and to create all possible ETCS messages and telegrams associated to each signal. The difference is that this information that is done and created within the application engineering process, it is not put into coders that are installed then on the field, but it is put within the server, a trackside server, which is the digital map. And so regarding the process, it doesn't change that much compared to a current ETCS level 1 process. And we can certify, of course, this method and the data that are coming at the end of the process. Next slide, please. The step 2, here comes the challenge, because we were discussing about application engineering. This is okay, we know how to do. Step 2, we need to get the state of the signal and to extract the state of the signal from the physical environment. So here we have different challenges. The first one is to find in the physical environment the next signal that is indeed addressed to us, because we can have situation on masts with a lot of different signals for different tracks. Think about exit of depots or of stations where you have a lot of different signals. So we need to find the right one. This is the first challenge. The second challenge, once we have identified the signal that is addressed to us, is to extract the state that the signal is displaying us. Of course, to do this this use case, first we can rely on new technological approach on computer vision side. So this is more expertise on supplier sides and so on. And then on our side in Toro, in the system architecture, we need also to define all possible information to reduce the complexity of the perception. So typically, the location of the signal is known because the signal doesn't move. So we know where it is on the track plan. The kind of frame, the all possible states that the signal can display. So this we know. And then the step 3, so here you have a complete overview and I will explain, is to perform the transposition, so to say, into ETCS format. So on a virtual point of view, this is the connection with digital map. You have properties of the track plan, but there are no objects on the track because we do not want to deploy anything. We can define in the digital map, so virtually, zones where infill is possible, like today in ETCS level 1 with loops, for example, and you can define information point. So here in this example, I have a signal 102, and so the only physical object on the track is the signal, and I have my locomotive approaching the signal. On the digital map, this signal is described with properties in the information point, signal 102, and the localization is provided with relocation balises that are also virtual. This you already may know, the concept of virtual balise and so on. This is something that is investigating since many years. We extract visually the information of the signal. So this is the eye and the visual extraction. So this is the pair device, perception. And when we have got the state of the signal, you can see this in the table at the right corner. For example, A for annonce in France, so yellow. you know, with the application engineering, that for this signal, when you have this state, then you have to apply this ETCS message because it has been identified by people, by engineers and automatic tools trackside in the data preparation process. And then the SCV, the building block in blue, will associate the signal state annonce yellow with, in this table, in this example, Telegram 2, and transfer this information to the onboard ETCS. And so, in the end, it is possible to virtualize existing concept of ETCS level 1. Next slide, please. So how it looks like versus a physical deployment. So basically the chain of information is quite the same. You have a light signal, for example. Today you install coders, so line-side electronic units, LEUs. These coders are programmed with application engineering data, so ETCS packets, and then it is transferred thanks to Eurobalises to the onboard. Here we do a parallel stream with another approach. It's not a technological approach with the perception, visual perception, and the conversion with the SCV, signaling converter, that is helped with the application engineering available trackside in a server. Next slide, please. And so in the end, what are we talking about? We are talking about complete ETCS level 1 virtualization. And the interesting part is that we do not address in Toro only one use case. This discussion is already happening in other working groups. And it is already a user need to avoid having too many physical balises, for example, in ERTMS level 2 or level 3, only for fixed messages. And so the need of reducing the amount of balises and to have ETCS messages coming from the digital map, so from the cloud, basically, thanks to the pinning of the train with the onboard localization, this is something already discussed. What we do in Tauro, and this is the Tauro scope in orange in the end, is that we complete this use case of virtualizing the balises with the switchable information coming from the signals, with the perception, with the onboard perception. And so you see that somehow the use case and the architecture and the concept is consistent with existing works in IP2, X2L4, and also needs expressed by users to reduce the amount of balises. And so thanks to all this technical answer, it is possible to have non-equipment trackside ERTMS on the physical point of view, and to protect the train, and also to have as a co-product the ATO on board. The next slide, please. An important aspect of what I am presenting to you is that, of course, we are dealing with the concept, and in Tauro, we enable the disruptive technologies with the system architecture. But what I am presenting you is already demonstrated in projects. So the first project that has demonstrated this use case is Train de Fret Autonome, so autonomous freight train in France, where you can have the perception of signals and the conversion of the signal aspect into subset 026 compliant information. And then with a converter box, this information subset 026, so ERTMS, is provided to ATO with the standard interface ATP ATO that has been defined in the previous Shift-ORel projects. So it is a demonstration for driving for ATO, JOA2, it's not for ATP, but the concept of perception of signals is demonstrated. The other project is in the Netherlands, sorry, with CAF signaling that worked with NS to demonstrate also the possibility of using the current ATO over a TCS standard solution on lines only equipped with the legacy system ATB as class B. And they used also the visual perception of line side signals to enable the use of ATO on lines that are not yet equipped, as a matter of fact, with ERTMS within the Netherlands. So today, on the concept point of view and on the technological point of view, it is demonstrated on prototypes in a representative environment for GAWay2, not for GAWay4 right now. And of course, the way to proceed is still important with industrialization and so on. But we at Toro are enabling the use of a standard solution with a standard architecture and standard interface. Next slide, please. And so the key takeaways, clearly the key takeaways I would like you to remember after this presentation is that very important point today, the standard solution ATO over ATCS as defined in the standards and in the upcoming TSI will not be possible to use on lines that are not equipped with the RTMS. So for countries in Europe like France or Germany, or you have projection of 20% of the national network, only 20% equipped in the 10 next years. Clearly, it is a pity, and it will be difficult for users to use the solution and even to make it attractive, because the users want to invest ATO on rolling stock if the national network is only equipped at 20% with the RTMS. This is a matter of fact. So we need to define migration solution that are enablers for ATO over ATCS and enablers also for the equipment of trains with onboard ETCS. And so the concept we propose and the standard architecture and standard interface with perception of signals, conversion into subset 026 and feeding of onboard ETCS, clearly it is an enabler for ETCS, for ATO, and for the whole industry. We are not relying on any Class B system, of course. This is out of scope. And so the bet we are taking in the group is to say that what we are currently studying is exactly the same as ETCS level 1. It is just that 20 years later, we have new technologies and new approaches to deploy this kind of level on a virtual point of view, thanks to application engineering and servers. And so what we define in Toro, the standard architecture, it will use and it will be needed to have new technologies, disruptive technologies, computer vision, onboard navigation to reduce the number of equipment trackside, and of course the digital map, which is a key enabler to the use case and for ATO in general. And that's it for my presentation. Thank you for your attention.
Thank you, Bastian. We will see if there's any questions from the audience in the chat. So please welcome, ask your questions. And we do have a question. Let me try to read it. So the SCV will transform the line-side legacy system into subset grammar to leverage on the ERTMS kernel. This function was defined in the past as STM European. The STM European function was to transform the legacy ATP information into ERTMS information in order to leverage on the pure ERTMS onboard. Do you consider leveraging on the STM defined interface to dynamically switch from ERTMS line to legacy line, or do you consider only the run on legacy line?
So good question. In fact, it was an important debate in the working group on how to proceed with this concept and to consider STM or not. For now, what we are trying to do is to say that we are equivalent to ETCS level 1. So the conversion of national signaling principles is done at the application engineering level, so as current ETCS level 1 today, and the information provided to the system and coming from the digital map is already standard. So it is already ERTMS ETCS messages, and so both trackside in the digital map and on board with the future EVC, so to say, it will be purely standard. It will be ETCS level 1. full supervision. This is our bet. And so there are no elements pointing out national values or national principles, because they are already been abstracted and taken into account during the application engineering process.
Okay, I hope this answers the question. We have another one from Valeria. She's asking, are you experimenting the usage of artificial intelligence techniques for computer vision or onboard navigation?
So for onboard navigation, I cannot answer this question. I don't know, in fact, what the different projects in Europe have experienced. For the computer vision, it depends. There are some startups and companies in Europe that have tried the perception of line sight signaling based on AI systems. Typically, the trials of CAF signaling in the Netherlands for the use case was performed with AI-based computer vision. It is also possible not to use AI in the computer vision field. There are also companies trying not to use, because as you may know, today the AI is not recommended for safe applications. So this is the challenge. Both approaches are possible, and different companies have tried both in Europe.
Okay, thank you very much. I believe we are now at the end. So in case there is no other questions, I would just say once again, thank you to all the presenters and to the participants for being with us. And I would also invite you to stay for the closing remarks that will follow just immediately. So thank you very much and have a nice evening.
Good evening, everyone. Well, I'm very happy and glad to be back for the closing of this second day of the Innovation Days 2022 for Europe's Rail, together with our Head of Innovation Program, Giorgio Travaini. And we will look together at what has been happening today. Very interesting session on optimized infrastructure, digital services, and IPX with the system architecture and disruptive technologies projects who have shared with us their knowledge. So perhaps, Giorgio, you would be kind enough to share with us a bit of the outputs from these projects that were shown today.
Certainly. So good evening, everyone. As yesterday, for those of you who followed our webinar, we would like to focus more on the energy aspect that was touched across all the different presentations. So, but I don't want to dismiss also innovations that have been presented today. So shortly, I will just wrap up what I think it's valuable for us to discuss on the infrastructure assets part. We have seen that we can do radical new innovation also on assets which are in use for up to 100 years old, maybe more. So we can see that we can develop the new slab track that are modular. Modular is also a key word in Europe's rail. We will be looking into how to modularize the system and standardize, therefore, the interfaces, and all of these with the help of the two structures that we created, the system pillar and the innovation pillar. And already in the Shift to Rail projects, this modularity approach highlighted several advantages and benefits out of the solutions that you have seen today. In addition, in the infrastructure part, there is a lot of digitalization. And this is, you see, the old infrastructure. When somebody thinks of rail infrastructures, thinks of steels, think of mast, think of different things. but we need also to embed it, the digitalization, and the key part, it's really the maintenance one. And the maintenance is a cost driver for the rail system. This is something that we wanted to bring down in Shift to Rail. We want to continue to bring down in Europe's rail. And we had demonstration of prescriptive maintenance. And this is very nice because it's a new concept. So we are able now to predict what is going to happen, but we're going also to tell which action needs to be taken in order to make the railway system at the end more efficient. But then also we don't need to forget the user, as I mentioned in the introduction. And our user are those workers that are working along the line. We can digitalize so much, but there will be always be worker on the track. But we need to help them to have, let me say, a work environment which is more comfortable also for them. And we've been looking into skeletons and different kind of new automated technologies for doing heavy stuff work. And then we go into the energy part. We had a dedicated chapter in the Innovation Program 3, and you heard a lot today about the innovation that we were able to bring with different type of solutions. So a few type of solution I would like to mention. One is the flexible alternating current transmission system. So this has highlighted the potential to really balance better the network and the energy consumption, including with reactive power back to the grid and including voltage imbalances. This is what brings as consequence. It brings a direct consequence on the fact that you can improve also the penalties that today infrastructure managers have to pay in case of the system the energy system not being managed in the perfect way. And those energy bills at the end will only increase for two reasons. Not only because the energy price is increasing, but also because the rail traffic will be increasing. And so the utilization will require also a better energy management system. And when we speak about energy management system, we need to think also a better or a smarter way in order to measure it and see where, for example, we have losses. And this is the work that has been done also in IP3, well, the smart metering solutions. And we have seen also in different use cases. So this is also important. We're not just testing it theoretically, but we are testing it in demonstration activities. It was tested in Spain and in UK. Then we go to IP4. We are more fresh on the IP4 content, so I will go maybe a little bit less into the details. But IP4 is today bringing all across Europe pilot because we want to show the potential of this multimodal approach where rail is the common backbone. But for this, again, we're using IT solutions. We are showing that it is possible actually to share information across transport modes and bring it to the final user. This piloting will help us also to understand the technological limitation because we have shown the technology is possible to be achieved, but it must be scalable. It must be fast, the response to the customer. And so this is good. This is good. But the most important stuff is that we are able to convince the public transport operator that there are solutions. And then, of course, the financial legal arrangement needs to come up together, but we have a technical solutions. And then IPX, it was the end of this afternoon. So IPX shown different also the innovation that could bring digitalization mainly. We have seen different data set use and data augmentation, learning approaches, etc., which can be used also later on in the traffic management system and in the context also of the traffic planning. This will be very much useful for the work that we're going to undertake in flagship project 1 of Europe's rail. And then also we have seen a few stuff about blockchain. Blockchain is another, word that we heard in the past years. Especially now we are hearing in the crypto digital, let me say, a digital exchange. When we're talking of Bitcoins or Ethereum or all these digital money, that is a lot of energy consumption in creating those blockchains. And then also here, the proof of stake instead of proof of work is providing more energy efficiency. So also learning from the other community outside of the race system. And then the Tauro project, what it's the basis for the next GeoA4 solutions. So for the ETCS, so European standard solutions that can be used everywhere in all the lines. And this is important because in defining those type of architecture, now we can also test it out in real demonstration activities in Flagship Project 2 of Europe's Rail.
Fantastic. Thank you, Giorgio, for this insight into what we have seen this afternoon and making the link with the energy crisis that we're facing at the moment and how we contribute to solutions to this. I have a question for you, maybe that could be interesting to our projects, is they have put a lot of efforts in developing these innovative solutions and have come up with very creative solutions, good products that are ready to be taken up on the market. What would be your advice to them in ensuring that beyond the life of the project, the world still knows about their solution?
Good question. So it is very important that so first of all, during the project itself, a good exploitation plan is built. This is not only a legal requirement, but it's, let me say, something that should be the basis for each project in order to know what's coming next. And one of the few important things is also the communication and dissemination aspect about the demonstration activities, because the demonstration activities are first the means to convey together with the final client, the possibility to operate in a system, technical solutions that have been developed. So leverage from it, use this opportunity, and maybe ask also your client to make an advertisement about the successes that you have done in the demonstration activities. And then, of course, the life should not end at the project. We don't want to have nice prototypes in the shelves or, I don't know, in the yard or on the line somewhere, or then dismantled, etc. We are really pushing you to make use of these results as much as possible, bringing them into the market. There are also instruments at European Union level that will help you to push those innovation up, but of course it requires that you have indeed an exploitation plan, and then we can also help you out to figure out how you can really exploit. But I'm sure that most of you have a plan, and I think I haven't mentioned it in this conference, but I was very proud to see, for example, those kind of results already implemented in commercial prototype at, also non-prototype, but in commercial products showcased at InnoTrans this year. And this is, I think, also the evidence that the products, the solutions are entering to the products in the market.
Perfect. And this is why we're here. So very good. This will be applied and continued in Europe's rail projects that we are signing the grant of at the moment. So a good basis for the future exploitation and dissemination of those results as well. I thank you all for your attention today. We will be closing now the second day of the Innovation Days 2022. We will reconvene tomorrow morning. I will be with you at 9:25 to kick off at 9:30 with our last day, which will cover the subjects of rail freight and I'm sorry, I lost rail freight and traffic management. For very two long and interesting sessions. extensive sessions. We also have, of course, the possibility to have the Q&A. So remember that you are very invited regularly to exchange with us and ask us through Q&A. If you have questions as we're speaking now, you're very welcome also to send us instantly, but we will be sending an evaluation survey at the end of the Innovation Days. On Friday, it will be made available on our website and sent to all participants of the conference as from Tuesday. So on this note, I thank you, Giorgio, for your insight, and then we will see each other tomorrow morning at 9:25 promptly. Good evening to all.